Welcome to Structural Analysis 2 video series. Unit number 3, Flexibility Method. Lecture outline, Numerical Problem on Continuous Beam Part 2. So this is continuation of a previous video. So far what we covered the step number 1, degree of static indeterminacy. Then displacement corresponding to the redundant in the original structure. Also we seen the different release structure with the load, release structure without load with the Q1 is equal to 1, and release structure without load with the Q2 is equal to 1. In first video we covered a displacement analysis of a release structure. From first lecture or first video we know the displacement of a release structure in the direction of a redundant dql1 and dql2. We was calculated the flexibility coefficient f11, f12 and f21, and then we form the flexibility matrix. So this we done in a previous lecture. Now second part of a problem, let's form the compatibility equation or flexibility equation. dq is equal to dql plus f into q. Now we know the values, now put here. So 1 upon EI take outside, minus VB divided by minus 2 VC is equal to 1 upon EI minus 4860 and minus 12740 plus 1 upon EI, the flexibility matrix 72, 180, 180 and 576 into the redundant VB and VC. Now let's simplify this. Simplifying this matrix, we having the equation that is nothing but the (73) VB plus 180 VC is equal to 4860, first equation. 180 VB plus 578 VC is equal to 12,740, second one. Solving equation 1 and 2, we have the unknown. Q1 is equal to VB is equal to 52.67 kilonewton and Q2 is equal to VC is equal to 5.63 kilonewton. Reaction at support A. Let's consider upward reaction positive and anticlockwise moment MAB as positive. This is our assumption at A. At B and C, the redundant we know 52.67 and 5.63 kilonewton acting in upward direction. Now find out the vertical reaction at A, considering summation Fy is equal to 0 plus upward minus downward. So plus Va plus 52.67 plus 5.63 minus 60 and this point load minus 30, make it minus 30 is equal to 0. So we have Va is equal to 31.7 kilonewton. Now take moment about A and find out the moment MAB. So moment MAB is, we assume anticlockwise positive, so plus MAB. Then a moment due to the 10 kilonewton UDL, which is rotate about the point C in anticlockwise direction. So plus 10 into 6 into lever arm is 9. Next point load or reaction 52.67 rotate about C in a anticlockwise in a clockwise direction. So minus 52.67 into lever arm 6. Next is a point load 30 acting in a downward direction. So plus 30 into 4, and next is the reaction at VA reaction which is acting at A, and the moment will be in a clockwise direction about C. So it is minus 31.7 into lever arm is 12 is equal to 0. So we have MAB is equal to 36.42 kilonewton meter. Shear force calculation. Shear force at A is 31.7 kilonewton, at B 52.67 and at C 5.63 kilonewton. Now this 31.7 acting up, so let's look it up. 10 into 6, that means 31.7 minus 10 into 6 become minus 28.3 kilonewton. Minus 28.3 plus this reaction 52.67, we have 24.37 positive. Then there is no load, so straight line. Then minus 30, we have minus 5.63, so no load, there is a straight line, and which is then minus 5.63 plus this upward force 5.63, we have 0 at C. So this is our shear force diagram. Now find out moment at B, and which is nothing but equal to the moment at B for the BC span. To maintain the stability, let's find out the moment for AB span at B. So that will be moment for at B for the BC. So FBD for the AB span. So moment at A is this one 36.42 kilonewton meter. Shear force is 31.7 kilonewton upward, and at B 52.67 kilonewton up, and the moment will be in a clockwise direction. Let assume at MBA, we don't know its value. Now take moment about B, anti-clockwise positive and clockwise minus. So first is MBA moving in a clockwise direction, our assumption, so minus MBA. Next is plus 36.42. Next is a moment due to the reaction, and it is in a anti-clockwise clockwise direction, so minus 31.7 into 6. Next is a UDL moving in a anti-clockwise direction about B, so plus 10 into 6 into 3. Moment of this 52.67 will be 0, passing through the O, so is equal to 0. We have MBA is equal to 26.22 kilonewton meter at B, and which is same for both the span. Let's draw the superimposed bending moment diagram. First, let's consider the loading and find out the free bending moment diagram. So our load is UDL, and for UDL the formula is WL square by 8. So we have W is 10 into 6 square divided by 8, we have 45 kilonewton meter. It will be a second degree parabola. Then second is there is a point load 30 kilonewton, and for that formula is WAB by L. So W is 30 into 2 into 4 divided by L is 6 is equal to 40 kilonewton meter. So we have in a triangular fashion. So this is a free bending moment diagram. Now next is a draw the bending moment for the end moment. So first end moment MAB is 36.42 kilonewton meter. So to get the direction, put your pen over the span AB and rotate about A in a anti-clockwise direction. Our sign is positive, so anti-clockwise direction. After complete one rotation, the arrow coming up, so you have to show up 36.42 kilonewton meter. Now the moment at B, BA is minus 26.22 kilonewton meter. So keep pen close to the B and rotate in the, now there is a minus sign, so you have to rotate in the clockwise direction about B. So this is the clockwise direction. After one rotation, the arrow coming up, so you have to show the value of 26.22. And at C there is a 0 moment, because that one is a simply supported end. So then join these magnitude with the line. It may be inclined or straight line. So we having now the end bending moment diagram. Okay, so this is the portion which is not overlap, that you have to make hatching you have to do there. Okay, so this is about your superimposed bending moment diagram. Okay, thank you.